we're going to hear a little bit about a connection that I mentioned a long time ago, basically back in the first lecture of this quarter, even of the winter quarter, on the relationship between information and energy. Obviously, we've been focusing almost entirely on dynamics and information production and information storage, and we've really kind of developed the physics of information that has excluded thinking about energy. So that's what today's lecture is going to be about. Mostly sort of indicating how we're thinking about these things and sort of future direction. So Alec, Boyd, working in our group here, will talk a bit about what we call information engines.
All right, thank you. Hi, I'm Alec Boyd. Like Jim said, I'll be talking about information engines. Just so to get started here, for the past 2 quarters, you guys have been thinking about information a lot, thinking about what it means, thinking about what's inside these bubbles. When we do these Venn diagrams of information, we might sort of wonder, what's this quantity that we care so much about? What does it represent? Well, maybe a more practical question in a lot of cases is, what does information do? And it turns out that thermodynamics actually provides a partial answer to that question, an answer to what information does, because it turns out that it sort of interacts with energy. So thermodynamics treats physical systems with large numbers of elements, and for those systems it has these physical constructs such as energy, work, heat, and temperature, and very importantly, entropy. So, I don't know how much experience you guys have with thermodynamics, but I'm just going to go through a brief little introduction. I'm sure this will be repetitive for some of you, but nonetheless, I think it's good to sort of all be on the same page here. So, for a thermodynamic system with all these different elements in it, such as a box of gas with all sorts of particles in it, maybe a bunch of hot and cold particles being red, cold particles being blue, particles with different momentums and weights and kinetic energies. There's a lot to describe about that box, but in thermodynamics, we often reduce systems like that to a macroscopic observable, such as pressure or temperature or volume. And we can end up making relationships between those macroscopic observables. For instance, the ideal gas law is a relationship between 3 or, 4 of those macroscopic variables. We've got pressure, we've got number of particles, we've got temperature, we've got volume. And there's, gases obey this law when they're nearly ideal. So, with this understanding, we sort of define a macrostate as a collection of these microstates, which are these sort of microscopic different orientations that correspond to the same macroscopic observable. So if you have all these different orientations for this box, there can be all sorts of different orientations where these particles are in different positions and have different momentums, such that the temperature, volume, number, and pressure are all the same. The macrostate we describe with those macroscopic observables will have a number of microstates. In some formulations, we treat it as having this number of microstates, omega. So with that microstate, with those microstates, we often assume that each of those microstates are assumed to be equally likely. So the most likely macrostates are end up being the macrostates with the most number of microstates. And with this notion of microstates, we can define this quantity entropy which we label S, as Boltzmann's constant, K, times the log of the number of microstates. And the second law of thermodynamics basically reflects the fact that you're going to tend towards the most likely macrostate, meaning your system's going to evolve towards the macrostates, which have the most microstates, which means that the log of the number of microstates should always be increasing, meaning that your change in entropy should be positive for any isolated system. So note that we can actually sort of reformulate this definition of entropy by considering the probability that you're in a microstate, Si, S sub I. That, given that we assume they're all equally likely, the probability of being in the microstate Si is just 1 over the number of microstates. And then, if we sum over this probability over all microstates, which is just summing this, meaning multiplying omega by 1 over omega, you get 1. So then, we'll do the full thing. We have k log omega. This is just the same as minus k log 1 over omega. And then we just throw in this factor of 1 right here, and we can carry through the sum because all these logs of PSIs are the same. That should look familiar to you. That should look very familiar. In fact, we can totally reformulate entropy now, not just using Boltzmann's definition, but instead consider a system which has a set of microstates Si such that the probability of being in Si is not necessarily uniform. So we have this system with all these configurations and different probabilities of being in all those configurations. And the thermodynamic entropy is the same as was formulated on the previous slide. It's S equals minus K sum P Si log P Si. And this looks very similar to our Shannon entropy. It's got an extra factor of the Boltzmann's constant, and you're taking the log of a probability. In this case, the probability is of the probability of a microstate, whereas here you've got the entropy of a random variable. So you're taking the log of taking the weighted average of the probability of a measurement of that random variable. But they're similar in how they're constructed, and they're also similar in their interpretation. So for thermodynamic entropy, it's often thought of as a measurement of disorder. For instance, we say hot gases here are have much higher entropy because they're more disordered than an ordered cold solid. They have more entropy. This has a small amount of entropy. And for comparison, we say that the Shannon entropy, the entropy you've been dealing with, is thought of as a measurement of uncertainty or unpredictability. So for comparison, we have this string of bits generated from a highly unpredictable random variable. In fact, a fair coin generates this, and that has a very high Shannon entropy, whereas the string of measurements here is entirely predictable. And maybe I see it. Hopefully you see it. I see an analog between the predictability and regularity of this string of measurements and the order of this solid, and an analog between the disorder of this gas and the unpredictability of this series of measurements. So it seems like we have an analog to Shannon entropy in thermodynamics here. And entropy is going to play a big role in thermodynamics. So just a quick note, though. I mentioned the second law of thermodynamics, which is that delta S has to increase. But that doesn't imply that everything's always decaying to a state of thermal equilibrium. We observe systems that, that have increasing order all the time. Here I have a picture of an embryo. Obviously, we know these turn into much more ordered systems like humans. We observe it all the time. We've observed it in the class. The point that's important to remember for this whole talk is it's strictly isolated systems that must have increasing entropy, meaning a system that doesn't have any energy exchange or information exchange with other systems, because that's going to be sort of key to remember when we're considering different information engines. With that said, let's talk about the relationships between entropy, energy, and other statistical, mechanical, thermodynamic quantities. So, for instance, if you have the entropy of a system, it's often an increasing function of the energy. There are cases where this isn't true, but in many cases, regardless, it's going to be a function of the entropy. And this is a common way that the entropy will be dependent on the energy. And it turns out that the temperature, which is basically a reflection of how much the system wants to give up energy, a higher temperature object wants to give up more energy to its surroundings. If you have a hot object and a cold object, the hot object's always going to give more energy to the cold object, and the cold object gives to the hot object. So it turns out that the temperature is just 1 over the slope of this curve at any point. So if you're at this energy, your temperature is going to be 1 over this slope. And so that's one relation we have between energy, entropy, temperature. And we also have that once we have this temperature thing defined, we have a statement about the probabilities of being in various macro states. We have the Boltzmann distribution over, we have this relationship between the probability of being at energy 1 and energy 0. Which basically tells you that if you're more energetic, you're exponentially less likely to occur. But with that exponent being less harsh when you have a higher temperature. Now, this is another relationship that we know about energy, temperature, and entropy, which is that the change in entropy for a system, which is at a given temperature, is equal to the heat absorbed by that system over its temperature. Now, using that, we can consider this sort of system, which is an engine. So we have a hot bath here and a cold bath, and they interact with each other with this engine in between. And so heat is going to flow in this direction. And we have QH, and we can extract a little bit of that energy that's coming out of here as work. Something we can do something interesting with. Energy that we can use. And the work plus the energy going into the cold reservoir, the cold bath, should be equal to QH. But how much work can we get out? How much useful stuff can we get out? Is there any reason to think that we can't turn all of this energy into work energy, useful energy? Well, once again, we have a relationship based on our knowledge about the way that our information analog entropy, thermodynamic entropy, behaves. We know that because it obeys the second law of thermodynamics, and the work that you're extracting doesn't necessarily have to increase the entropy at all, you know that the total entropy of this system will just be, or it could just be the heat of the heat absorbed by the cold bath over the temperature of the cold bath minus the heat given off by the hot bath over the temperature of the hot bath. And that has to be greater than 0. So then you have this relationship for the two heats of the hot bath and cold bath, and the temperatures of the hot bath and the cold bath. And then we define the efficiency of this engine. The efficiency of this engine is the amount of useful stuff, the output, over the input. So the useful stuff is our work here, and the input is the heat coming from the hot reservoir. Well, that turns out to be 1 minus QC over QH, and because of this known relation, we have an upper bound on our efficiency here, which is imposed by the knowledge that entropy has to increase. So in general, this heat engine is an important thing it's a classic example of a useful fact that's derived from thermodynamics. And it's also interesting to compare to a general information engine. And this relationship is, I don't know, it's kind of beautiful that this is true for any sort of system you can construct, any arbitrary system. We have a constraint on the flow of energy, heat to work, based entirely on the dynamics of this information analog. So entropy is relevant to the flow of entropy. So now we move on to the real meat of the lecture, the information engines. So I'm going to cover 3 information engines. I'm going to cover Maxwell's daemon, which is a classic, the Szilard engine, which is much like Maxwell's daemon, but is a little bit more precise and covers some of the areas that Maxwell's daemon doesn't address very precisely. And then we'll cover the Mandal-Jarzynski model, which is a recently proposed model and is interesting because it's exactly solvable and very applicable to the tools we've been developing. So before we get into that, though, information engines, let's just talk about what they are relative to what we just saw. So we saw a heat engine. They leverage temperature differences in heat flow to do work. But information engines, to some degree, always use information to do work. They leverage information to do work. So here's Maxwell's daemon. So we have a box here. Here's our daemon right here. And we have a box, and it's filled with a gas. And there's a separator between the two sides of the box. And there's also this green little door here. The daemon has control over that door. And what the daemon does is when he sees a particle coming from the left that's slow, it's blue, so it's slow, and not very energetic, he keeps the door closed. But when he sees a hot particle, a fast particle coming in from the left, he opens the door and lets it through. And really, he also does the reverse thing from the other side. When you have when you have a hot particle coming in from this side, he keeps the door closed, and when you have a cold particle coming in from this side, he opens the door. Now, if you allow the daemon to do this, you end up, after some time, with this your steady state where you have all your cold particles on one side, all your hot particles on one side, and the system becomes, if it's isolated, you have this temperature difference here. And what did I just describe to you? I described a way to leverage a temperature difference to do useful work. You can extract, you can attach a heat engine between these two sides and power a car or something. So if you run the heat engine and the daemon simultaneously, you appear to have a machine that's extracting thermal energy from this gas and turning it into work. But the problem is, if you have the thermal energy of the gas decreasing, you also have the entropy of the gas decreasing. And the work doesn't have to balance that out anywhere. The work doesn't have to create any entropy. So it appears that the second law is violated. So to understand how the daemon could be consistent with the second law, let's consider what it's actually doing. So these are the fundamental steps of the daemon. First of all, it has to have some interaction with whatever particle that's near the door to measure whether to open or close the door. So here it sees a hot particle and it has to have some interaction with it that allows it to decide whether to open the door. Same with the cold particle. And also the daemon needs to decide to open the door or close the door. But also, this is a part that people sometimes forget about if they're thinking about the computation that one of these daemons does. If the daemon has finite memory and if it's performing this process repeatedly, it needs to be able to forget what it measured. So it needs to go from the aha state, I know whether you're hot or cold, to the I'm going to measure again state. And so it needs to be able to empty its memory register, erase its memory register. Yeah. So then once we see what the daemon has to be doing, we can start trying to balance the second law of thermodynamics by saying that there has to be some sort of cost to one of these processes. For instance, maybe there's a cost to measurement, an energy cost to measurement. For Brillouin, I don't quite know how to roll my R's or anything, so I don't quite know how to say his name. But he thought that measurement was the way to resolve this problem, because if you have a box, or if you have a system that's at a temperature T, there's going to be black body radiation. And the photons in that black body radiation are going to have energy around K times T. So what the daemon has to do in order to recognize a particle as being something more than its black, or as being something more than black body radiation, is it has to send an extra energetic photon at the particle, doing some work. This is one perspective on how to resolve this problem, that you have to do at least KT of work to resolve that there's a particle, that there's even a particle there. But it turns out that we won't get into this. It turns out there are cases where there's not necessarily a measurement cost. But the more standardly accepted perspective is that there's a cost to erasure. Landauer and Bennett both argued for this perspective. And the idea behind it is sort of that if you have a memory with two states or more, there needs to be some separation, way to separate those states, to prevent one state from evolving into the other due to thermodynamic fluctuations. And thermodynamic fluctuations will happen on the order of kT. So that means that this energy barrier that separates this zero state from the one state, or the right state from the left state, whatever it may be, that must be at least, the height of that barrier must be at least kT. And then when you erase, you need to map to a new state. You need to map to your default reset state. So if your default reset state is your zero state, you need to basically half the time get this the one particle over this barrier to the zero state. That's sort of the intuition for it. But Landauer's principle sort of formalized this from a different perspective, not really using mechanism, but using the second law again. And he stated that the minimum amount of energy required to erase one bit of information is kt log 2. So the way to see this is if you have one bit of information, you have two states with equivalent probabilities, and we assume that the two states 0 and 1 are symmetric, meaning that for every state, microstate of the, say, 0 macrostate S0, there is a twin microstate S1 such that the probability of S1 is equal to the probability of S0. And then you can evaluate what the initial entropy of this distribution is when pi, or when the initial probability is equally 1 and 0. So we have the sum of the the entropy of the 0 states and the entropy of the 1 states. But since these are these probabilities are equivalent, you can just combine them into the one sum over the probabilities of the 0 states, and just add a factor of 2 out in front. And then for the final state, you have that the probability of being in a 0 for the final is 1, because that's our reset state, and the probability of being in the 1 state is 0. And since we're going to map each one microstate to its twin 0 microstate, so the probability of each 0 microstate is twice its initial probability for the final. And then we just evaluate the change in entropy of the memory. We have the entropy of the final minus the entropy of the initial. We have the sum of these two here, and then we use this relation to substitute in for pi here, and then we end up with this sum of over the 0 states of the final probabilities. And it turns out that this all works out to just be a change of minus k log 2 of entropy. So the change in entropy of the memory is minus k log 2. That means that the change in entropy of the environment to compensate for this change in entropy of the memory has to be at least k log 2. And that means that the heat that flowed into the environment from the daemon, which is the heat of erasure, has to be T times the change in entropy of the environment, which is KT log 2. And then by energy conservation, the work done for erasure has to be equal to the heat of erasure, and that is also greater than KT log 2. So the Landauer's principle is pretty commonly thought to be the resolution to these information engines. But there's sort of a problem with it in that it's vague, in that it doesn't really provide any mechanism for erasure. It just assumes the second law and then states that it's necessary to do this work in order to satisfy the second law of thermodynamics. And I think we are pretty concerned with mechanism in this class. So just a general overview of this daemon is that it's good because it's intuitive. It's a classic model. It's the first thought experiment that really brought up this issue of computation doing work and the problems associated with it. But the problem with it is that it's not easily derivable what the memory state of the daemon is. Like, we don't know how uncertain we are about its memory state, and we also don't we probably could derive it, but we don't necessarily know how much work we're doing a priori by this using this engine. So we introduce the Szilard engine, which is similar to Maxwell's daemon, but like I said, covers some of these gaps. So again, consider a box with a particle in it. And, well, before we had a box with many particles, now we just have one particle. And then without performing any work, slide a thin barrier separating the box into two halves. So this is our green barrier again. Again, we can slide it in with no work. And then, again, we do an observation. The daemon observes which side the particle is on, such that it can decide which way to slide this barrier. It can slide this. It will always decide to slide the barrier away from the particle. Yeah, do you have a question? No. Okay. It will always slide this barrier away from the particle, and in doing so, gain some work. And when I say it slides the barrier slowly, I mean that it's sliding the barrier isothermally, meaning that the particle inside the box is always able to equilibrate with the environment that's surrounding the box. So it's able to bounce off the walls enough to gain a thermal energy to compensate for the work that it's doing on the wall as it pushes it. So in that way, you're sort of transferring the thermal energy of the vibrating walls into work energy by expanding the wall away from the particle. And then once the barrier is on the opposite side of the box, you remove it, and the daemon forgets what it's done. And you're at your start state again, and you can repeat the process over and over again. And once you've forgotten your measurement without any, you can just, you can repeat the process. So we couldn't evaluate this for the Maxwell's daemon, but let's talk about the work that the Szilard engine does. So you can do this over and over, but for one step, you have this work. And we use the ideal gas law, which I mentioned before, and you have two pressures. You have the pressure on the left, which is the number of particles on the left, which is 1 times kT over the volume of the left. And then you have the pressure on the right, which is 0, because there are no particles on the right. And the work extracted is the integral of this pressure over the change in volume of either side. So here you have integrating 0 over this change in volume. And here you're integrating this pressure over the change in volume from V0, which is this area, to 2V0, which is the whole area of the box. And it turns out that that integral works out to be kT log 2. Yeah?
Can you briefly discuss why that's a reasonable thing to do to ideal gas law?
Oh, because this particle is not interacting, we're saying that it's moving ballistically around, so over long times the average force that it exerts on this wall is going to be the same as if many, many independently moving particles were in that box. Does that answer your question, or are you asking a different one?
I think that's what I'm asking. So the one assumption that you're having to make is the one about the isothermal.
Yes.
Nature, and
that you're moving the wall very slowly so that you're essentially averaging all the collisions of this particle as if it were many, many, many particles. Yeah?
So looking at this, it seems a bit that the problem's been massaged to get the KT ln2 because we're going from V0 to 2V0. What if we went to 3V0 or 4V0? Then we get a different amount of work extracted,
Right. But if you did that, you wouldn't necessarily be erasing a bit. We'll get to that later, but if you went from, if your box was extended like 2 sections to the right, you know, your probability of measuring on the left section and the right section would not be equivalent, so your stored information would not be the same. And when you did store that it was on the left, and you did more work, it would be a more unique measurement, so your
So you,
yeah.
okay, so it comes down to at the beginning the knowledge entropy of left
Yeah.
or right.
Yeah.
And different ones. Okay.
Yeah. I mean, we could go into that case,
It's-
but
yeah, it kind of makes some sense.
okay. Right. So I think we're done with this slide. So continuing on. So yes, like I was telling you about, since there's 1/2 probability that when you insert the barrier, the particle's on the left as it is on the right, or those are both 1/2 probability cases. The probability that the daemon is in the left measurement state versus the right measurement state after measuring are both 1/2. And thus you have two equivalent measurement states for this system. And according to, if we accept Landauer's principle, then you have that since the daemon has to reduce its entropy by k log 2 to reduce its entropy enough to return to the default state, you have that the work that the daemon has to do to erase that information is greater than or equal to kt log 2. So that means that the total work of this system, which is the work of the particle done on the barrier, minus the work done by the daemon to erase, the total work of this cycle, even if each portion of the cycle might not have 0 work, it has to be less than 0. So we're not turning thermal energy into work, and the second law of thermodynamics isn't violated. Yeah?
So it seems like in this case you're having the daemon do the work, right? And in the Maxwell daemon case, you had the environment doing work on the daemon, right?
The daemon, right. So what I mean, are you talking work erase or work particle? Work erase.
Yeah.
In either case, there is some work that has to be done on the daemon, or some way for the work to go into the daemon such that heat flows out of the daemon. Should we go back to the slide to make this clear again?
So is the daemon doing the work in this case, or is it?
It's either you or it's either you or the daemon. So the fundamental thing is that some heat is flowing out of the daemon. That's what's fundamental. So ultimately there needs to be some energy flow into the daemon, like either from like some energy store that the daemon has, or like some work that you're doing as an external person on the daemon itself to compensate for this, right? Does that answer your question? I mean, this is I think the thing to focus on. Maybe there is some work that's done to compensate from this, and where you put that work, whether it's inside the daemon or outside the daemon, either way, it's done on the system. It comes from somewhere. Because you can't just like all of a sudden release heat energy into your environment if you're at the same temperature as your environment. It needs to come from somewhere. So the work is done by something. Not necessarily the daemon. Where were we? We were here? Here. We were here. Right. No, we were here. So the total work that's coming out of the system has to be less than 0. Right, so that means that we aren't turning thermal energy into work. So we aren't violating any laws of thermodynamics here, if we accept Landauer's principle. So just to get a full picture here, let's consider the whole process, and let's create a joint representation of the daemon and box, because it might not be necessary to think of the daemon as being separate from the box, ultimately. Let's think of them both together. So here we have the representation of what's happening with the daemon. It's either, it doesn't know what's going on with the particle, or it does, and then we have the various steps of what's happening with the box and the particle. And then we have this Markov model, which contains both the state of the daemon, with the box state being the first digit and the daemon state being the second digit. 0 represents the left, 1 represents the right. And the first thing you do is you let the particle equilibrate with the box, meaning that its distribution becomes uniform over the box, so you have 1/2 probability of being on the right side and 1/2 probability of being on the left side. But the daemon, in either case, is in its default state, in its reset state. And then you insert the barrier and do a measurement. So here you've inserted the barrier, and the daemon doesn't know what's going on, and then it does a measurement. It's like, it's on the left. And in this step, you move from the reset state for the daemon to the state that's synchronized with the box state. And then you do the work extraction and equilibration process. And in this process, again, you split states into states in which you have or in which you have 1/2 probability of being on the left, 1/2 probability of being on the right, 1/2 probability of being on the left. And you do it for both states here. And then, finally, the daemon resets. It goes back to not knowing what's going on. And in this case, this is the only part in this Markov model where you have multiple states going to a single state here. So whatever the daemon state was, you map it to a 0. And then you end up finally in the same state as your initial state. And you can go through this again. So this is just a tool to try to see the daemon from a different perspective. But there's still some problems with the Szilard engine. Again, there's no mechanism for erasure or measurement. It's just assumed. You just say the daemon does erasure, the daemon does measurement. Who cares how that happens? And another interesting, maybe it's not a problem, but an interesting fact is that with an infinite amount of memory, according to our interpretation of the daemon, you could extract all the thermal energy out of your box and do work with it, which seems like a problem, but may not be. But the really, the thing I think really problematizes this model is the idea that when the daemon measures, it needs to also decide, the daemon needs to, when the daemon has the particle in one side of the box, it needs to decide which way to move the box. It can't just let the box expand on its own. Why do we need the daemon to decide a direction? What if we have a symmetric system? What if we symmetrize the daemon? And by this, I mean, consider this model. What if instead we insert our barrier from the top? It's the same, except we insert our barrier from the top, and we have these strings attached to the barrier, and we have these little rollers that the strings can go along here. And this is 180 degrees symmetric, so right and left, really not necessary to specify here. And then we just allow the pressure exerted by the particle to move the wall here. And that movement, combined with the pressure of the particle is going to do work by pulling these strings as they move along the rollers. So the same or nearly the same work will be extracted without any measurement or erasure in this process. So is this daemon, or this system, doesn't seem to be balanced. So is this machine impossible? Is there any reason why we should just dismiss this machine out of hand? I'm not sure. But ultimately, I think the problem comes down to the fact that the constraint, when we're making machines like this, that we have these thought experiments about what sort of machines we can use, the constraints aren't unclear. The constraints about what things we can create are sort of unclear. We need sort of a canonical model for what a daemon is, but because if we don't, then we just end up with things like this, which seem plausible, but we can't pin down why they're wrong.
Really quick,
Yeah.
just before we get too far away, I'm just curious, is there a reason why we know that the process can be isothermal, as you were calling it, where it's in constant thermal equilibrium?
Is there a reason why we know it can be isothermal?
Yeah, I mean, it seems to me like, how do we know that that is even possible in that situation? When there's just one ball. I mean, if it's really going in random directions, chances are it's going to hit the ball or the wall multiple times before it equilibrates, right?
Yes. Yeah. Well, it will. I think the idea is that it hits the wall so many times that by the time it equilibrates well before the majority of its collisions. Does that make sense? I think that's the idea behind the argument.
I was thinking in this case, if it's pushing out the wall, it's going to lose some energy every time it pushes out the wall.
It's always going to do that if the wall's moving away. But the point is, oh, I see what you're saying. If the wall is moving away, well, still, if it's moving away very, very slowly, equilibrating is yeah, it will likely still equilibrate at very nearly the temperature of its surroundings. Does that make sense?
Okay. I'm
But
not sure.
this is not a bad question. Just to be clear, I've actually looked at a particle in a box numerically and analytically, and you may remember this. And there are some issues with equilibration when treated classically.
You
But-
do something like thinking of like a billiard problem or something. Where
Uh-huh.
You don't just have a box on the left, but you have a little passageway. The passageway leads to a large equilibration chamber. So you very likely go back into the chamber, equilibrate, but then only very unlikely when you come back
Right.
out to do more work.
Right.
Because here it seems like about a fourth of the time you're going to come back and hit that. So there will be some temporal correlations between the various strengths.
Mm-hmm.
I mean, at the very least, you'd want to have some kind of chaotic shape.
Yeah.
Or something like that.
Yeah, that's interesting. I don't know. That seems like something to investigate. The frequency of collisions. I have to say, with numerical calculations, I wouldn't say anything I've looked at would indicate that that's not the case. That it's not a problem to have this thing moving. But yeah, this is all an example of like we can throw around these models and try to be as simple as possible and say this is how it works. But then you come up with these problems like correlations between collisions that make our estimations seem, I don't know, silly. But anyways, let's move on to a different model. So the Mandal-Jarzynski model. This is pretty recent, I think since 2012 or 2011. So it's a very different type of engine, information engine. There's no assumed erasure or measurement process. That makes me kind of happy. And the benefits of the model are that it's exactly solvable. So even though there's no assumed measurement or erasure process, while we're looking at this, I kind of like you guys to think about, does measurement happen and does erasure happen? Is there some step in this process where you're like, that's erasure right there? or something like that. So, so the Mandal-Jarzynski model is all based on a wheel, 3 states along its edges, and this wheel can rotate, I believe it's counterclockwise twice. So it rotates 1/3, 1/3, 1/3, 1/3, 1/3. And that's as far as it can rotate in this direction. It can rotate backwards also. So it can just move, thermal fluctuations kind of just make it move along in that state space. And for each of these states, we'll just label them with the state that corresponds to the bottom node, or the bottom ball right here. So we have A, B, C, and also with the a 0 if you haven't gone through a rotation, and a 1 if you have. So you go A0, B0, C0, A1, B1, C1 in terms of states. And just this gives us this network model for how you go through state space. This sort of represents how you have neighbors between the different wheel states. And I've elevated the 1 states, the 1 rotation states, because if we suppose that there's a weight attached to this wheel by a string, there's an energy difference between the 0 and the 1 level. And that energy difference is the mass of the weight times gravity times the change in height that's associated with 1 rotation of the wheel. When you allow this system to undergo thermodynamic fluctuations between its states, it should have a steady state distribution of e to the, or the probability of the 1 state over the 0 state should have the steady state distribution. That's the Boltzmann distribution here.
I'm imagining as it's drawn that every third rotation also shortens the string, raises the mass. So don't you have 6 different energies?
You would. That's not how the model is constructed, though. So maybe a model. Imagine the wheel such that the string only moves up when you move from, say, A1 to C0, or C0 to A1. The reason this sort of makes sense is because we're going to consider a collection of rotations, and you can either go from 1 to 0 a certain number of times, or 0 to 1 a certain number of times, and those will average out to be captured by single rotations. But yes, if we were going to be absolutely literal, that's the correct distribution.
I'm having trouble physically interpreting something like this, but I'll go with it for now.
Okay, fair enough. So now we start considering the dynamics of the probability distributions over all the states. So we have our vector, which is a probability of being in state A0, B0, C0, A1, B1, C1. And the thermal fluctuations jiggle the states around in the way I described before, and that is described in this vector form by having the derivative of the vector be equal to the vector times some rate matrix, where the matrix contains transition rates between states. And this rate matrix looks like this. Note that it's only got diagonal elements and off-diagonal elements, which reflects the fact that you only have transition rates between nearest neighbors and yourself. So all the diagonal elements are negative, meaning that once you're in your state, you can only transition out of it or stay in it, or you have some probability of transitioning out of it. But also notice that we have this epsilon factor right here. And this epsilon factor parameterizes the energy difference between the 0 states and the 1 states. So there's a rate difference between going from A0 to B, or A1 to C0, and there's a difference, rate difference from going from C0 to A1 and A1 to C0. And this has a steady state distribution that's proportional to this.
Which was high energy? 0 or 1 is more high energy?
1 is more high energy.
So why are they more probable?
Well, I'll just say epsilon is negative. I'm just copying from the text, or from the paper. Anyways, thus you find that epsilon has this form in terms of the Boltzmann distribution, because we know that the Boltzmann distribution has to be obeyed. And now that we have this rate matrix, given that we have an initial state V0, we can get the final state after a time tau with these thermal fluctuations just by operating with e to the r tau. So that describes the thermal fluctuations. You could probably change this matrix, this rate matrix, to reflect more appropriate continuous rotations. But ultimately, the interesting part is talking about the input tape, because there's an additional part of this model is that it has interactions with a tape here. So for the interactions with this tape, you have an input tape here, and then you have an input bit on this tape, and then you have an output tape. And the tape moves in this direction. And as this tape passes by, the wheel interacts with each interaction bit for a time tau. And during this interval, the wheel evolves as described by the Poisson process. So the wheel state and the interaction bit and wheel state always reflect each other. So if the wheel state is 0, then the interaction bit is also 0. Similarly, if the wheel state is 1. So to put this all together, we also consider switching of bits. So we have, at the start of the interaction interval with this bit, we have that you're at A0 and you have a 0 at this bit. And then you evolve according to the thermal fluctuations, and let's say you end at B1. Now, that means that the interaction bit changes to a 1. And then you switch the bits. So this new interaction bit, you move this tape to the right once. That now becomes part of the output bit string. And the new interaction bit is the old last input bit, and it's a 0, so what was formerly B1 now becomes a B0 to reflect what the input bit was at that time. The machine writes new information to the output string, but the input bit also changes the wheel state as it comes in. Yeah?
So when the wheel is just moving, you can only move stepwise from state to state through our network. But when we move the tape and then force the wheel to synchronize, we can move anywhere within the wheel state space.
No, you move only to the exact same wheel state. So if you're in B, you have to move to B. You just move to the level that corresponds to the input bit. Does that make sense?
Okay, so there are two different transition structures here.
Yes, exactly. Two different transition structures. So with this structure, we can reduce to a three-state system where we just have a vector of the probability of A, B, and C, where the probability of, say, A is just the sum of the probabilities of A1 and A0. And we start by, if n is the index of the interaction, then we start by defining Vn prime by just projecting onto whichever states correspond to our input bit. So for instance, if our input bit is 0, we operate with the projection onto the 0 states, which is just the 3 by 3 identity matrix followed by the 0 3 by 3 matrix. Similarly, for the 1 state, we have the 0 3 by 3 matrix followed by the identity 3 by 3 matrix. Once we've projected onto the 6 state system, you bounce around according to the thermal fluctuations by operating this e to the r tau matrix, this Poisson process matrix on Vn prime. So Vn double prime is Vn prime after projection and after the thermal fluctuation process. You look confused.
Yeah, so the identity matrix, as in like the ones all down the diagonal?
Yes.
Why would you need to multiply that by matrix? Wouldn't that just give you the nice
So this would map, this matrix would map this to the matrix where you have 3 extra zeros on the end. And this would map this to the vector with 3 extra zeros here. So you're mapping to the 6-state system such that you can apply this thermal fluctuation.
Oh, okay. I think I get the notation now.
Okay.
I wasn't seeing what that meant. I guess.
All right. Cool. All right. And then you project back into the 3-dimensional basis by multiplying by the transpose of the 1 projection matrix and the transpose of the 0 projection matrix, which basically just maps the 0 states and the 1 states back to the non-index states. So you map the probability of A1 plus and the probability of A0 to the sum of their probabilities in the corresponding element. So what this gives us is a probability of output given input. So we have, for instance, if the input bit is 0, the probability of that the output bit is 0 is our current state times the projection onto 0 with some fluctuation, then projected back onto the 0 states, then summed up by operating on the column of all ones. Same idea for all these others, where the first projection corresponds to the input and the second projection corresponds to the output. So what this gives us is the exact form of a transducer. We have this set of transducer matrices where we have the input I, output J is given by Pi e to the r tau P J transpose. And this gives us the form of the probability of the output equals J equal given input equals I. We just operate the matrix on our state and sum using the column of all ones. And this also gives us our input I. Given an input I, our state after interacting with a bit. So if our bit is I, like I said, the state Vn plus 1 is just going to be the transition matrix the corresponding to input I that has output 0 plus the transition matrix that has input I corresponding to output 1. So what this thing is it's an object that maps input strings to output strings, arbitrary input strings to arbitrary output strings. So we can put any string into it, input string, as we had in our model, and get a new output string. But let's limit ourselves to biased coins as our input. And from that, we can get a hidden Markov model for the output, given by t to the j is given by, so for the output j, you have the matrices, the probability of input 0 times the transition matrix for input 0, plus the probability of input 1 times the transition matrix for input 1. And in general, these hidden Markov models look as follows, with varying coefficients here. So now let's talk about the work that's being done. So if you have if your input is the same as your output, that means that the wheel didn't undergo a full rotation. So if you started at 0 and ended at 0, or started at 1 and ended at 1, the work that the wheel did was 0. However, if you started at 1 and ended at 0, that means that your wheel went down in energy. So it ended up doing negative work. Work equal to negative the change in energy of the mass. Whereas if your input is 0 and your output is 1, that means your wheel lifted the mass such that it gained delta E. So then you can get your expectation work. It's just the probability of your input and your output times the work associated with the input and output. And so here you have that it's just delta E times the probability of input 0 and output 1 minus the probability of input 1 and output 0 plus 0. I just added this term because it's 0, and it ends up being convenient because the probability of input 0, output 1 plus input 0, output 0 is just the probability of input 0 right here. And the minus the probability of input 1, output 0 minus output 0, output 0 is just minus the probability that your output is equal to 0. So this is easily evaluatable right here. This is the probability that your input is 0 is just given to us by our assumed bias. And the probability that output is 0 is something you can get from the Markov model. So what if all our inputs are 0? So that means that the probability of input equals 0 is 1. And the probability of output is less than or equal to 1, just because that's the condition for any probability. So therefore, according to this equation, we have that the work is greater than or equal to 0. And in fact, there are many parameter values for which the work is positive. These gray regions are all the places where this thing is doing work, lifting this weight on average with every time that it goes through its cycle. And this is just epsilon, which we discussed, and this delta is just 2 times the bias minus 1. Just to make that clear. Yeah?
Do these results on the slide of the previous depend on the type of input, or just the probability of 0 and 1?
They depend on the type of input, I believe. Or wait, this slide? Which results are you asking? Are they?
The last line, does that depend on the fact that it's a bias point or not?
No, I don't think so. No, this is true regardless of whether it's a bias coin or not. Yes, so now what has been done is comparing work versus a certain type of entropy. So we've introduced an entropy per we introduce an entropy per input bit and an entropy per output bit. So we have the entropy per input bit is just the standard entropy evaluation times the probability of the input bit log p of the input bit. And there's a change in string entropy that's just, there's a change in single symbol entropy given by S out minus S in. And a result that I wouldn't expect you guys to be able to derive because it's a major result of the paper that presents this, and it's derived partially numerically, is that the total work, the expectation work here, is less than or equal to the temperature times this change in single symbol entropy. However, this means, right, so the thermal fluctuations have done this work. And this means that the bath loses that expectation value of W in thermal energy with this process. So that means that the change in entropy of the bath is the change in thermal energy over tau, or over the temperature, which is just equal to minus the expectation work over T for every step in this process. And so for every step in this process, we have the change in S total, which is equal to the change in the entropy of the bath plus the change in entropy of the bits, is just minus the work over tau over the temperature plus the change in entropy of the bits, which, as we showed before, obeys this relation. So it turns out that the change in total entropy, as defined here, I wouldn't actually call this total entropy. I should just consider this quantity right here, is greater than 0. So that it appears sort of like we're satisfying the second law by writing information to a memory output. Or writing to our output string. But the entropy per bit, is that really comparable to the entropy of the bath? And to illustrate why I'm dubious about this is, again, consider this string that we previously discussed as being highly ordered. But this expresses maximal single symbol entropy output entropy. So making sure that the sum of that and making sure that the sum of single symbol output entropy and the change in entropy of the bath is greater than 0 for every step is not really a very strict condition, and wouldn't necessarily be equivalent to saying that the disorder is always increasing. So better metric than the entropy per bit would be the entropy rate, for which we need the epsilon machine. So the hidden Markov model that I showed you before, which typically looks like this, is really quite non-unifilar. You really don't know what your next state is given your current state and your measurement, because, for instance, if you're in the A state and you measure A0, you could go to A, or you could go to C, I believe? No, C, or you could go to B. B, right here. So it's very non-unifilar, so we need to do a mixed state reconstruction. But when we do our mixed state reconstruction to any length that we've tried so far, the states don't merge for most of the parameters. There are some special parameters for which you get very simple engines, but for the large majority of them, for uncountably many of them, you get this, it appears. So we need to plot what we get on simplices. So this is this is the plot of the mixed state as on the simplex of the A, B, and C. On the A, B, C simplex. These are two different systems, though, just to illustrate that there are sort of differing behavior here. And in neither case do we seem to approach a finite set of states that would imply we have a finite epsilon machine. It seems we have an infinite epsilon machine for most representation, or for most parameter values. So, relating their entropy to work at this point is kind of in progress. It's kind of interesting. If you're curious about it, I could talk to you about it. It involves evaluating things like fractal dimension and things like that. But what we do know, though, is that the single symbol entropy is an upper bound for the entropy rate of the output. And that the single symbol entropy for the input is the same as the entropy rate because we have biased coins. Thus we know that the change in entropy of the bath plus the single symbol entropy is greater than the change in entropy of the bath plus the change in entropy rate. So we're not guaranteed that this is greater than or equal to 0 by previous results. So that's something that still needs to be looked into. Anyways, so just to step back with this model, I guess, is this the same sort of information engine as the Maxwell's daemon and Szilard engine? I find it hard to really make an analog between the engines, but it's very clear that it's using information to do work. It seems to be writing to a register. I don't know if any of you guys have any opinions after seeing how it works. But it does ask, we do have a lot of questions we can ask now that we have a hidden Markov, a transducer model for this system. We can ask what are the roles of various statistical probabilities that we've been talking about in this class. Like what's the role of the excess entropy, or like the entropy rate, as I mentioned, or the transient information. How does that relate to the work done? What are these quantities for the input versus the output string? And for treating it more as a transducer, what's the mutual information between the input and output strings? How is that related to the work done? And what are the differences in quantities? How do they relate to the work done? So, I guess if there's a big thing that I wanted you to take away from this is that it seems that information transaction can do work. I feel like these were 3 models that I showed you where information processing allowed work to be done, even if the net work of the system was 0. So there seems like there's some exchange between the two types of quantities, work and or information processing and energy. So I guess we're left with more broader questions about the future, not just about the Mandel model, like something I mentioned before. What are the constraints on physically achievable models? We keep on coming up. We have all these models that we're not exactly sure if they're realizable in physics. So can we come up with constraints on hidden Markov models, such as maybe detailed balance, which is a term that's common to both statistical mechanics and what you guys have been learning, and also causal reversibility or irreversibility. So also, what sort of constraints on transducers could there be? And just to throw something else in there, I mentioned earlier that it would be nice to have a canonical representation of what an information engine should be. And there's actually been some progress here done by Sagawa and Ueda in pursuing that idea, because they took the quantum mechanical perspective. And in quantum mechanics, the idea of an arbitrary time evolution and arbitrary measurement are actually well formalized. So they actually found that there was a, rather than saying that there's just measurement or just erasure that's necessary to balance the information or balance the work done by a system, they found that it's the sum of those. Sometimes it's measurement, sometimes it's erasure that's needed to account for this, or account for the work done. So with all this, I guess maybe you'll start to see the potential for investigation into the intersection between physics and computational mechanics, and thermodynamics and computational mechanics, because I'm pretty curious about what physical computation is and what are the constraints on it. So that's